right, so path or no path?
You didn't ask.
Is the consensus no path?
I'm sure you have a consensus.
I get 2 votes, that's all.
Can we please?
I think there is a path, but we haven't found it.
What did the numbers mean?
What does anything mean? Okay, so this turns out there's no path, which also means there's no circuit because a circuit is a path.
Because I did get it, except for one edge.
Yeah. So we'll see why we can tell there's no path there in a moment. What about this one? Is there an Euler path?
There's a path.
What would be a path?
A, B, E, D, C, A, D, B.
So A, B, E, D, C, A, D, B. That looks good. Cool. Is there an Euler circuit? Is there a path that starts and ends at the same point? Turns out there's not. Alright, so there's a theorem which is due to Euler. So a simple graph G has an Euler path if and only if exactly 2 or 0 vertices have an odd degree. So if the number of vertices with an odd degree is either 2 or 0, you're guaranteed there's an Euler path. So in this case, we got 1, 2, 3, 4 vertices with odd degree. That tells you there's no path. And the second fact has an Euler circuit if and only if all vertices have even degree. So if all your vertices have an even degree, there's an Euler circuit, which is also an Euler path. If exactly 2 vertices have an odd degree, there's an Euler path but no circuit. In the other case, there's no path, no circuit. And in our examples, right, so here, this was a vertex with degree 3, and this was also a vertex with degree 3, and our path began and ended at those vertices. And that's always going to be the case. And if you kind of wave your hands at it, right, whatever vertex you start at, as you leave that, you're going to have one edge coming out of that. And maybe at some point you get back to it, right, which now you have 2 edges. If you're not done, you're going to have to leave it, which means you're going to have 3 edges. And maybe at some point you come back through it. And if you're not done, you're going to leave it again, so then you're going to have 5 edges. And unless you end at the vertex you started with, the degree of this vertex is going to be odd. And exactly the same argument can be made for the vertex you end at. But any other vertex, right, once you enter it, you're not beginning or ending there, so you're going to leave. Each time you visit that vertex, the degree goes up by 2. It starts at 0, so it's always going to be even number of edges, and when you're done with your whole traversal, the degree will be even. And if it's a circuit, right, you end at the same place that you started, and so that argument applies to the starting ending vertex, so that has an even degree also. And it's those odd degreed vertices that cause you trouble. All right, so those are Euler paths and Euler circuits. We can also talk about Hamilton paths and circuits. And Euler was a mathematician, 1700s, I think, and there was a set of bridges in Germany, and there were islands that the bridges connected. It was like a walking path, and there was always this question of, is it possible to cross all the bridges exactly once without repeating? And that's arguably where this work was first done. I don't know how much of that's urban myth. So a Hamilton path or circuit contains each vertex exactly once. So Euler path circuits, you have to go through each edge exactly once. Hamilton path circuits, you go through each vertex exactly once.
And you can have it so it's both a Hamilton and Euler.
And you could have both, yes. So first one, Hamilton path.
Yes.
Yes. So A, B, D, E, C. Perfectly fine. And we can actually come back to A. And there's a Hamilton circuit. So that's a path. Yes, and a circuit, yes. All right, how about this one, Hamilton path? A, B, C, D. Hamilton circuit? No. Yikes. How about this one, Hamilton path? No. So definitely not a circuit. How do we know there's not a Hamilton path here?
If you start at A, you can't get to both F and G without going back to where you started.
If you start at A, you can't get to both F and G without going back to where you
So
started.
to go to, if you started at A,
Mhm.
and you go to F, there's nowhere to go, and you can't get to G. Or
Right.
if you go to G, you can't get back, and there's no way to get to F.
Right, so we're going to get stuck. All right, and we could make a similar argument if we started F or G. And if you started one of these interior points, then you just got three places where you're going to get into trouble. But in general, given a graph, to tell whether or not there's a Hamilton path or circuit is a really hard problem. And there's no nice general criteria like there is for an Euler path or circuit. It's a much harder problem.
Is there any possibility where there's a Hamilton path where you have three isolated?
I don't think so. If they're really isolated like this, I don't think there's any way that you can visit those.
Because two works. I don't know
Yeah,
what
if
they-
there's two, you can go. Yeah,
And it doesn't matter whether or not there's two on the same level.
right.
You can just do a weird, like, square wave.
Yeah.
So it's the three isolated that.
Yeah, so three isolated, I think, will tell you right away there's none. But there's other graphs that are harder to look at and apply some kind of logic to, but they may not have a Hamilton path. So that's a hard problem. Let me give you an example of an application of Hamilton paths. So I'm going to draw a graph. So there's a graph. It looks like it's three-dimensional, but it's just a graph. And I'm going to label my vertices in this kind of funny way.
Date protection.
What?
It's computer stuff.
Oh, cool. So I've got 8 vertices. I've got 12 edges. I've got my vertices labeled in this peculiar way. And it turns out there is a Hamilton path through here. So let me show you. I'm going to go down like this. I'm going to go up. I'm going to go back. And I'm going to scoot across. There's a circuit. So there's a Hamilton circuit through this graph. So the way I've labeled these vertices was not random. If 2 vertices are adjacent to each other, if they're connected by an edge, do you notice anything about the labels on those 2 vertices that might be interesting?
They're only different by 1.
Yeah, they share 2 bits in common and they differ by 1. It may not be the first 2, right? So these 2, for example, the last 2 bits are the same, the first bit differs. Here the first and third bits are the same, the middle bit differs. But they're always the same in 2 bits. So only 1 bit changes as we move from any vertex to any other.
Yeah, that's what computers do to keep
Yeah.
them fragmented.
Yeah. So since we have a Hamilton path, we have a way following edges to get through every vertex. We've got every 3-bit number sitting on a vertex. This Hamilton path tells us how we can move from one 3-bit number to another such that exactly 1 bit changes each time that we move.
Isn't this gray code?
This is gray code. So if we write down these vertices in order along this path, we get that. And as you move from one number to another, only 1 bit changes.
But that's only a really
Oh,
small. Usually they have like much. This one's only 3D. but-
Yeah. So you could do this for really big bits. And this is called reflective gray code because, so you remember, none of you took 120 with me. When I teach 120, I don't know about others, we teach how to count in binary. So that's 1 bit. If you want to count 2 bits, just repeat that. Put zeros on the top, put ones on the bottom. So you've seen that, right? So we can repeat that. Put zeros on the top half, put ones on the bottom half. So that gives you your regular binary counting. To count in reflective gray code, we do the same thing, but when we repeat, we flip the order. So we do 0, 1. Here we put 1, 0. And we put zeros on the top and we put ones on the bottom. And if we want to go 3 bits, we repeat this, but we reflect it. So there's our 1, 0, 1, 1, 0, 1, 0, 0. And we put zeros on the top half and we put ones on the bottom half. There's your reflective gray code. And this is really useful in computer science, especially Engineering 250, because if you have a state machine and you're moving from one state to the next, you don't have race conditions. Because at most 1 bit is changing. Now over here, if this is state 3 and this is state 4 and we want our system to move from state 3 to state 4, you got 3 bits that have to change. And what happens if this bit changes first? You go from this state to this state, and then maybe you go to this state, and then eventually you get to your final state. What if this, state 7, is the panic launch all missiles state? And you went from, it's morning time to it's time to start making coffee, and accidentally launched all the missiles because you had a glitch in the system. So if you use gray code encoding for your states, that doesn't happen, and you get to enjoy your coffee. And so that's one way to look at Hamilton paths, right? It's a walk through your binary combinations.
look like in the three dimension. So the original gonna be 0, 0, and this way.
Yeah, so I think the way that this is laid out, this looks like X, and
Y.
this looks like Y, and that's Z,
Yeah.
which is even right-handed, so that's good.
What's the shape if you do 4-bit number?
Hypercube? I don't know.
So,
You
I
can
was-
go higher and higher dimensions.
Yeah,
so
I think they
0,
use like 8th dimension stuff
yeah,
for most.
cool.
So 0, 0, 1 is gonna be go right side one step and
Yeah,
keep the
yeah. Yeah, so that goes over in X, and that one's X, Y, and Z. All right, we got time to start Dijkstra's algorithm. And this is like useful in your daily life. Okay, maybe not. So Dijkstra's algorithm is a way to find a shortest path through a weighted graph. So we're going to have a graph, but we're going to have weights on each edge that correspond to how long it takes or how much it costs to travel along that edge or something like that. And the question is, what's the lowest sum of weights to find a path from one point to another? So typical example, you have a bunch of cities, you have a graph where an edge corresponds to a road from one city to another, and the weight of that edge is how far you have to travel along that road. And so here's your starting point A, and there's B and C and D and E, and maybe there's something like that. And maybe this takes you 10 minutes, and this takes you 5 minutes, and maybe this takes you 12, and this is 7, and this is 20, and this is 15, and this is 4. Not drawn to scale. So this is a super duper high speed interstate, right? So clearly your quickest path from A to E would be to go along this edge right here, right? But it could be that there's some some super fast highway roads that like warp space or something, and you can go from A to F in one, and from there to G in one, and if you follow this path, you can get from A to E in a total distance of 1, 2, 3, 4. And even though there's a path with a single edge, the path that has 4 edges ends up being faster or shorter, right? So when we talk about length, we're talking about adding up the weights of each of these edges. And so there's no sort of quick look at this and tell what the shortest path is, right? You can't just reason it as the number of edges. And so a breadth first search, like when we find a Bacon number, is not going to work, because that tells you the shortest number of edges, but taking the weights into account changes that. So Dijkstra was a mathematician, computer scientist, who came up with this algorithm. Story about Dijkstra: when he applied for his marriage license, they wanted his occupation, and he put down computer scientist, and they told him that's not a real occupation, and he had to change it to mathematician. Because computer used to be somebody who sits at a desk and does computations. It was a job description, and so computer scientist doesn't make sense. It's like teacher scientist. Doesn't mean anything. So, but you can get jobs in computer science now. Okay, so Dijkstra's algorithm. So Dijkstra's algorithm only works if the weights are restricted to being non-negative. If you're allowed negative weights, this does not work, which is interesting. So this could be, cost, and maybe you get some money for traveling in that direction, or toll booths.
But does it work with 0?
I think with zeros you're okay, but negatives totally wreck it. Okay, so let's make a sample graph. We're just going to go through this algorithm. I'm not going to describe it in pseudocode or anything. We're just going to run through an example, and then probably Wednesday I'll have you work on some of these at the board, because you'll almost always see one of these on the exam.
Hint, hint.
Hint, hint. Or maybe a quiz. We'll see how it goes on Wednesday. All right, so there's a graph. We've got 6 vertices, and we're trying to find a path from A to Z. So we need some weights. So there's a 4 and a 2 and a 1 and an 8 and a 5, 10, 2, 3, 6. All right, so we're starting at A. We want to find the shortest path to Z. And you and I can do this. We can look at it and we can keep some things in our brain. And most people can eventually find a good solution just by kind of looking at it for long enough. But we want something that we can teach a computer to do. Okay, so we have this very specific algorithm called Dijkstra's algorithm. So here's what we do. So visit first node. So visiting a node means drawing a green circle around it. Okay, so we're going to begin with a node that we're coming from. Write tentative distances to each vertex. So what's a tentative distance? It means with what we know right now, which is nothing, what's the best possible case that we can say will suffice to get us to any vertex? And for now, that's a purple infinity. So we're going to put infinity next to each vertex. But for node A, we know we can get there in a distance of 0 because that's where we're starting from. So this is all we know right now. We're starting at node A. This is as far as we've gotten. The distance to every other vertex is no worse than infinity. Right, infinity if it was unreachable for some reason. Okay, so now we're going to loop. So we do what's called a relaxation step. So relax distances to reachable vertices. So we're sitting at node A. We know we can get to node A. If we were to just follow one edge, what can we get to? We can get to node B, right? And since we can get to node A with a distance of 0, and this edge has a length of 4, we know we can get to node B in a distance of 4. Okay, big question. Is 4 better than infinity? Yes. Okay, so we're going to relax that distance, which means we're going to take that infinity and replace it with a 4. And I'm going to write down the path that gets me there, which is start at A and then go to B. Okay, what else can we get to directly from A? C, total distance, better than infinity. Okay, so for a distance of 2, we can get to node C by starting at A and going to C. And that's all that we can get to directly from A. Okay, so next step, visit the closest node that we haven't already visited. So we have nodes at a distance of 2, 4, infinity, infinity, and infinity. Our closest node is a distance of 2. That's node C. So we're going to visit that. So visit means we're going to put a circle around here.
In a computer, how would you denote infinity?
You could use a
In this
flag.
sense.
Probably use a flag.
Say unreachable.
Yeah, yeah. That would be safer than like a really big number. All right, so now we just go back and we repeat this. So relax any nodes that are reachable at this point. So what can we reach from vertex C that we haven't already visited? So we can get to E, right? And we know the distance from C to E is 10, and we know the distance to get to node C was 2. So 2 plus 10 is 12. That's better than infinity. So now we can reach node E from a distance of 12 by going through whatever we take to get to C, which is A comma C, and then going to E. Ace. From C we can also get to node D. Takes 2 to get to C plus another 8. That means this takes a distance of 10, and the path is A, C, and D. All right, from C we can also reach A, but we've already visited A. We don't care about that. We can also reach B. And we've seen B before, but we haven't visited. We haven't circled it in green, so we want to consider B. Well, from C to B is 1, and the distance to C is 2. 2 plus 1 is 3. Is that better than 4?
Yes.
Right, so we're going to relax this and say we can just get here with a distance of 3, and the path is A, C, and then B. And those are the only nodes we can reach. And so now we're going to pick the closest node and mark that as visited. Well, 3, 10, and 12 looks like 3 is the closest, so we mark B. And we just keep doing this. Now, once we visit a node, what we're saying is this is the shortest path, or a shortest path. Right? From A to B, the shortest path we can find is going to be length 3. And here's one way to do that, ACB. And it's shorter than the one edge path, which had a length of 4. All right, we got a few minutes. Let's finish this up. You getting the idea?
How would that work if you had, say, like A to Z, and A to Z was like a direct like that was like 10, and the other path was a series of ones that added up to like 15.
It'll end up. Oh, if it adds up to 15.
Like there's a one, like a bunch of paths that are 1, so it's the shorter path to take, but it ends up being longer.
Yeah. So this will find the one with the shortest total length.
Okay.
Yeah, and that would be a good one to try. So when we play with this on the board Wednesday, we'll try some pathological examples. All right, so we visited B, so what can we get to from B? We can get to A, that's visited, C is visited. We can get to D, 3 steps to B, another 5 steps to D, that's 8. That's better, so let's relax D. So D takes a distance of 8, and the path is to go to B, which is ACB, and then go to D. And that's the only thing we can reach from D. So what's our shortest unvisited node? 8, 12, and infinity looks like an 8. So we'll circle that. And now let's relax from D. So we can get down here. 8 plus 2 is 10. That's better than 12. So we're going to relax node E and say this is only a distance of 10, and the path is ACBD, followed by E. And we can also do 8 plus 6 is 14. That's better than infinity, so relax that. And so for a distance of 14, we can get to Z by first going to B to D, which is A, C, B, D, and then going to node Z. And now find the closest node that looks like our 10, node E, so visit that. And repeat this, and from E, the only unvisited node we can reach is Z. 10 plus 3 is 13, that's better. So relax this, 13, and we get there by going to E first, which is A, C, B, D, E, and then visiting node Z. And that's the only node we can reach, so now find the closest node that we haven't visited, that's node Z. So we're going to mark Z as visited. And in this case, we're trying to reach Z. As soon as you mark that node as visited, you can stop, because you found a shortest path. But if you wanted to find the shortest path to every node, you could keep going until you're out of nodes. Same thing here. So what have we done? We found the shortest path from A to Z. And it's not a very direct path. It's just start off at A, come down to C, go up to B, go over to D, come down to E, and then go up to Z.
Is this what most direction apps use?
Probably some variant of Dijkstra's algorithm, yeah. It's a really simple algorithm to code once you've done it a few million times, which other people have.
So in our example, we just took the shortest path each time, but that's kind of just a coincidence.
I think that's a coincidence.
Okay.
Yeah.
Okay.
Let me see if there's a quick way to rectify that.
That's sort of what I was asking, because if there's a longer path, you would just avoid it.
Yeah.
Even if the series of shorter ones end up being longer.
So
You
if,
avoid the last platter.
so if this was a 1, yeah, we'll have to come up with an example for that. But yeah, picking the shortest path doesn't necessarily get you there.
Right, because if there was a chain of ones that went off.
Right,
tangent,
right, yeah,
Just a coincidence that in our example that's not working.
right. So that's Dijkstra's algorithm. And it's straightforward to code if you have a good way to store your graph and you can find things that are adjacent, right? So an adjacency matrix works well for that. And you just update what you're storing in your structure so that you can record things like weights of edges, and visitation, and tentative distance, and what the path is to that. So you can do linked lists inside a matrix, inside something else, and it's all good fun. All right, so we'll play with this on the board on Wednesday, and then we'll start talking about languages and automata.